Okay, today in this session, we'll start discussing about exercise questions of topic 1. So I will start with E1-1. I will start with E1-1. Let me just read the questions first. Okay, the magnetic fields, the magnetic circuit shown in E-E11 has dimensions of AC equals to AG equals to 9 cm square. Okay, G, which is the gap, G is not something like gravity or something. G is gap. The gap is 0.05 cm. LC is the mean path, the mean path of the core, which is 30 cm. N is number of turns, which is 500. Assume that the value mu R is 70,000 for core material. The question is A, find the reluctances RC and RG. For the condition that the magnetic circuit is operating with BC equals to 1 Tesla, find B the flux phi and C the current I. So we'll start with finding the reluctances of this magnetic core, which is, we can convert this to magnetic circuit actually. Okay, so this is a core. As you can see, this arrangement of core, as you can see in figure E1-1 here, we have current flowing through, passing some of the coils or the windings, windings, and then go up. Okay, from top of the wire, you can see the current is flowing in and flowing out the bottom. So we have an n number of turns of the coil, and we have this core from material like ferrum or any material. Okay, so this is the core, and we have the air gap. We have the air gap here with the magnetic permeability of mu naught and the area of AG. Okay, and for this core, for this particular core, we have a magnetic permeability of mu and area of AC, area represented by AC. So this is a general representation of the values or variables used for this particular arrangement of core with the air gap. Okay, so we are going to discuss this in terms of magnetic circuits. Actually, we can convert this particular circuit to the magnetic circuit, like something like this. So we have MMF. So we have MMF, something like that, which is equals to Ni. We have R1 and R2. R2 means something representing the reluctances, which is, in this case, we have RC and RG that represent the reluctances of the core and reluctances of the gap, the air gap. Okay, so we can convert this particular arrangement of magnetic core with some coil in it with the magnetic circuit like this. All right, so we have all of the values of AC, AG, gap, LC, the mean path, LC, and N, 510, so on and so forth. So we have all of that values. So I write down the values here, which is AC equals to AG, which is 9 cm square. G is 0.05 cm, LC is 30 cm, and N is 500 tons. And UR given is 70,000. So some of the values you see here is in cm, cm and cm square. So first thing first, we'll need to convert the values to meter, which is the standard measurement. standard SI unit for when we do the calculation. Basically, we will convert it to SI unit first. Okay. Let's say for 9 cm square here, we can convert it to meter square. Yeah. Okay. For 9, let me just write down another page. Okay. Because we have some of the values we need to convert first. Okay. First one is AC equals to AG equals to 9 cm square. You know how to convert 9 cm square to meter square? Because some of the student they cannot do. That's why I'm going to show you how to convert 9 cm square. This is basic math, you know. 9 cm square to meter square. Okay, basically if we want to convert this, we just write down 9 cm square, and what is 1 meter square? So 1 meter square is 100 times 100 cm square, right? So here we can just cancel cm square so that we get meter square, right? So in this case, we have 900, we have 9 divided by 100 times 100 meter square. Okay, so 9 divided by 100 times 100 meter square, which is 10,000. So here we get 9, here we get 0 0.0, 0 0.0009. Okay, then we can just write it as 9 times 10 to the power of -4 in meter square. Okay, so we have converted value of surface area of the air gap and the surface area of the core material. Not the surface area, it's area, which is cross-sectional area. Cross-sectional area of the core and cross-sectional area or surface area of the gap, AG and AC, represented in meter square. Okay. So we have another value in cm as well, which is which is G goes to 0.05, right? No, now I'm going to convert G equals to 0.05 cm to meter lah. So just simply convert it, which is 100 cm equals to 1 meter. So we get 0.005 in meter, or G is 5 times 10 power of -4 meter. So that is the air gaps, the air gaps, very thin gaps that appears across this magnetic core. Okay, and do we have any other cm LC, which is 30 cm, right? So convert it to meter divided by 100. Okay, so we get 0.3 meter. So that is the mean path length. The mean path length, the average line, the average path. Let's see. Okay, let's say I start from here. Can you see that? Mine cannot make it as a pointer. If it starts from here, from the middle of the core, somewhere in the middle of the core, it will pass through at the average line of the core. Okay, so it will like a perimeter, something like that. Okay, so we have mean path length over the core, which is 30 cm in this case. So we have converted it to 0.3 meter in meter. So we have all of the values in cm has been converted to meter. Then after that, we can proceed with the calculation. And also given, okay, let me just write down everything here. BC is also given. BC is 1.0 Tesla. BC is magnetic flux density. And then also all of you should know that mu naught. Mu naught is magnetic permeability of the vacuum. So 4 pi times 10 power of negative 7. So mu naught is 4 pi times 10 power of negative 7. Okay, now we want to find RC and RG. Okay, we want to find RC and RG for this particular core, right? For this particular core, we can convert it to magnetic circuit like this. So we have MMF at the left hand side. This is MMF equals to Ni. Okay, so from this MMF, because of the current that we give to this core, because of the current I and N number of turns, we have MMF of Ni. So this MMF will be pushing some flux, flux flowing through RC and RG. So this is the something like resistance, analogy to the resistances, which is RC represents the core reluctance and RG is the air gap reluctances. So we want to find RG and RC now, which is this is RC and that is RG. Okay, the same for this figure and the other figure. RC is the core reluctance and RG is the air gap reluctances. So what is RC and RG? We can just use the formula given. If you go through my other tutorial videos and also lecture, okay, for RC and RG, we can just compute it by using the formula. For RC, we start with RC equals to LC divided by mu R, mu naught surface area or cross-sectional area of core, which is AC. Okay, that is RC. Similarly for RG, it is G, which is the gap, divided by mu naught AG, cross-sectional area of the gap, the air gap, or air gap surface area. Just write it. So AG is air gap surface area. So for air gap, why is it mu naught saja? Because in vacuum, for the air gap, it is no relative, no relative. It's air gap and the vacuum. Air gap, vacuum is mu naught, and for the air gap, mu R is 1. Okay, so for the air gap, actually we have let's say if I put some mu r here, mu r is actually 1. So mu r equals to 1. That is why I didn't write it. Because for the air gap, we can just use this formula. We can just use this formula directly. For the core material, of course, it should have some relative permeability times the mu naught. Okay, so this is mu. Let's say for iron is iron punya mu lah. Okay, so iron punya mu adalah mu r mu naught. Okay, let's say this is iron. You can just use this formula. So RC, RG, we have the formula and we have all of the values, LC, mu R, mu naught, AC. Similarly for RG, we have value of G, mu naught and AG from the questions, so that we can just substitute the values to compute RC. We start with RC first. So RC, just substitute all of the values, LC, mu R, mu naught, and AC. So we have RC equals to, LC is 0.3 divided by mu R is 70,000. Mu naught is 4 pi times 10 power of -7. And also AC is 9 times 10 power of -4. Okay. Then we get the, I just skip the calculation. You can just use your calculator. 0.3 divided by 70,000 divided by 4 pi times 10 to the power -7 and divided by 9 times 10 to the power -4. Then you will get 3.79 times 10 3. Okay, 3790 lah, 3790 ampere turns unit for reluctance, ampere turns per Weber. So this is RC, yeah, this is RC. So how about RG? How about RG? I'm going to move this. Okay. How about RG? How about RG? Again, do the same thing what we have done for RC, which is just substitute all the values given, which is G is 5 times 10 to the power -4 divided by mu naught divided by mu naught, which is 4 pi 10 times 10 power of -7 times AG, which is 9 times 10 power of -4. Then we get RG, which is 4.42 times 10 power of 5 ataupun 44,200 kan, 1 2 3, ataupun dalam kes ni 442,000, betul tak? 442,000 ya. Manakala yang atas ni, kalau kita convert kepada, sekejap saya nak adjust yang atas ni. Okay, saya nak convert dia kepada, supaya boleh nampak dengan jelas. 379,379,0 3,790 for RC, reluctance for core, for the core. But with that small air gap, which is 0.005, 0.0005 gap, it turns out to be the reluctance, as you can see here, which is 400. 3, 4, 5. Betul lah. 442,000 ampere turns per Weber. It turns out to be 442,000 ampere turns per Weber of the reluctance of the air gap. Can you see the difference? Even though we have very small air gap here, RG is quite high. Is more than 10 times. More than 10 times. Just see. Not 10 times, more than 100. More than 100 or 1,000 times lah. Tengok berapa besarnya beza RG because of that small air gaps yang ada dalam. That's why in construction of the transformer, construction of the machines, electric motor, we will try to minimize the air gap to make sure that less reluctances to make our motor or transformer more efficient. Okay, that is RC and RG for question A. For E1-1A, right? So this is A, yeah? For B, okay. For B, for the condition that magnetic circuit is operating with BC equals to 1 Tesla, find B, the flux, find flux. Okay, we want to find flux. For B, we want to find flux. Flux is B times A. In this case, we are referring to the core. We are referring to core, which is the flux passing through the core. I'm going to draw again and again so that you are familiar with. So we have this phi passing through this core. Because of what? Because of we relate, we do some windings. Change the color. See, because of the windings with current we supply of I and one windings of N. Because of this, what we call as magnetomotive force. So the flux will be flowing through this core. Okay, the flux will be passing through this core. Okay, so that flux is analogous to current lah. Analogous to current in electric circuit, and that flux also can be represented by the magnetic flux density times to the cross-sectional area or area of the core, which is in this case we can represent it as BCAC. So now we have BC is 1 Tesla and AC is also available, is also given, which is AC is 9 cm square, right? So just simply for this particular question, you can just substitute the value that has already been given in the question, right? So phi equals to BCAC, which is BC is 1.0 Tesla times AC, which is 9 times 10 power of negative 4, 10 negative 4. So flux is unit in Weber. So we get 9 times 10 power of negative 4 Weber for the flux. Okay, that is B. So the last one is C, right? Which is the current that is flowing. How much current here? Okay, we can relate this current by using F equals to Ni. By simply using F equals to Ni, and we know the MMF, and we also know the we don't really sure about F, okay, but we have N equals to 500, right? We know N, so this is 500, N is 500. How about F? Okay, so actually for this particular equation, we can just convert it to, F equals to phi R, right? You remember that? This is analogous to V equals to IR in electric circuit. So this is electric. You use this analogy, this is magnetic circuit. So we use this analogy. F, which is MMF, this is MMF, is analogous to V, which is EMF, electromotive force. F is magnetomotive force. For the current, it is analogous to the flux, okay? And for the reluctance, it is analogous to the resistance in electricity. So we can compare this. You can just remember this. How we can understand the use of analogy for that one. Okay, so F equals to Ni, so we can just convert this F, which is phi. In this case, for the MMF, we have MMF that is from this side. Can you see that, the pointer? You cannot see clearly, but MMF start from the windings. Okay, winding. It will be pushing some flux, passing through this magnetic core. Okay, magnetic core passing through this iron core, and then pass through this air gap, and then back to the MMF. Okay, so in that case, we should consider not only R for the core, but also R for air gap. So in this case, we have R core plus R gap equals to Ni. Okay, let me just move this to another part here to make it clear. Okay, to from here to there. So we want to find current, right? We want to find current. So just convert this equation. to I equals to phi RC plus RG divided by N. Alright. So we have that sort of arrangement of equation. Then what we can do now is just substitute the values. Okay, we substitute all of the values given. We know that phi from B, from B we have already got pi. Sorry, we have already got phi, which is 9 times 10 to the power negative 4. How about RC? How about RC? It's 3790, 3.37, sorry, 3.79 times 10 to the power times 3.79 times 10 of power 3. Okay, let me check it by one by one. 3.79, 4.42 times 10 power 5. Is that correct? Okay, divided by N. N is 500. So tekan calculator. If you want to do more calculation, just convert that one in the bracket. 0.0379 times 10 power of plus 4.42 times 10 power of 5, like that. Point 45. Okay, so 9 times 10 power of negative 4. Where is my border? That is my border. Okay, this is my border line. When I convert this to PDF, you know, it should have some border lines here. So I hope it will not cut some. Okay, so from here we can just further calculate. We solve in the bracket, inside bracket here, 4.42 plus 0.0379 akan jadi 4.45 lah, betul tak? 4.4579 lah. You can turn on your mic if I got wrong. If I got wrong, just turn on your mic, just let me know.
Okay, doctor.
Okay, thank you. Okay, so we have 4.4579 inside the bracket times 9 times 10 to the power negative 4. Then we get this one is actually let me do this first. Okay, just put it a bit down so that I can divide this by 500. Divide this by 500. Okay, now just push your calculator. Finally, you get I equals to, in this case, we have 0.8 ampere of current. So we supply 0.8 ampere of current to this 500 number of turns. Turns out to be the flux. Flux of phi equals to this one. Okay. Turns out to be this flux flowing inside this core, passing through this reluctance of the core and reluctances of the A gap, which is reluctance of the A gap and core is given in A, right? So that's all of things we have already finished calculating for A, B, and C given in the question E1-1. Okay. Okay. This is exercise E1-1. Moving on to exercise E1-2. I will use another canvas. So for exercise 1.2, this is the question. Before that, let me just stop the recorder for